Okay, my wonderful students, let's begin lecture. We're going to have 4 lectures from here to the end of the semester, and then the final. And for us, the final's coming up really fast, right after the last lecture. So we're going to return exam printouts. Tricia just grabbed them. But before we do that, I want to go over a few of the answers from the clicking items on the test. Here's one of the questions, and I don't know, maybe you can take notes on this. Can you get the section 2? The exam printouts. Hold on a second. All right, leave the scantrons in there. Just take the exam printouts. Okay, let me see this. Hold on a second. Let's get the top sheets off here. Grace Acosta. Good. We're going to look for those. How many have a PID error, does it say?
3 of them.
Okay, so that's those 3. They're going to be down here at the bottom. So take those back out, because what I want you to do now, that's these 3 unknown students. So while I'm teaching, I want you to figure out which student goes with which. Okay. All right. And then when you figure it out, write their name on the printout.
There's actually 5.
Yeah, but those ones some of them have no test form. So just figure out, see, there's 2 that have no test form, right? Is that what that says?
Yeah.
Okay, so we can't do anything with those. So that's that one. No test form. And that one has a test form. Okay. And maybe this one, it might be too light. But now see this little really light number down here? That corresponds to the form serial number. Okay, so you look for 152, 204, and 221 down on that little, okay? And then write the name on these. All right, sorry. Yeah, let's get back to business here. The clicker question, you may have noticed I've been increasing the complexity of the clicking. The first clicking task, it's been using symbols in a code table. This time, your objective was to write a full sentence. Well as you could do, given that we don't have a full dictionary of words and tenses and everything like that. Why can you conclude logically that Procyon A has a higher surface temperature than our star, the sun? Now, the way that I grade this, it's similar to the previous 2 exams. I decode each. Can you cut the volume down a little bit on this? Good, thanks. I decode each sentence, all right, from symbols to a readable sentence, and then I read everybody's sentence. I mean, for this class, I had about 270 sentences to read. It didn't take me that long. And so then I assign a grade, 0, 1, 2, 3, or 4. 1, 2, and 3 are partial credit, and in this section, there were a few students that got 1, a few students that got 2, a few students that got 3. The full credit, 4 points for a good sentence, there were 87 students in here, so that's almost a third of the class. So that's really good. Actually, it's very close to a third of the students who took the exam. And of those sentences, there were 70 of them different. Now, I want you to think about that. You guys wrote the sentences, not me. And I decided that 70 of them were good. All right? Now, since I'm not a computer, I'm a human being, I can interpret small deviations and awkwardness, especially in this system. We only had, 20-something symbols to use. So, you can't, Shakespeare would not be able to write a sonnet, nor would you, and it come out gracefully. But even though the sentences are awkward, and we're going to look at some here, you'll want to take notes on them. I can still, being a human, I can interpret what you mean by doing that. So what we're going to do is take a look at some of them. And it's kind of interesting. I was intending everybody to be looking at this one. But a couple of you guys answered in terms of the HR diagram. And that's lovely. And I gave full credit for the students that did that. And a couple other variations that I consider pretty cool. So here's the question, as you know. And here, go ahead and jot down this code. There it is, PJWQVDWR. That's kind of a long one. And here's, you probably don't remember what you typed in, and I don't know whose this is. I could look it up, but here's what it is in straight decode. All right, now that's got all the parentheses in it and stuff. So it's a little awkward looking. So here's cleaned up a little bit. All right. So here's one student's answer. Procyon A's peak is filter band B compared to Sun's filter band V. And this student got a 4. I considered that to be a good result because that student, they weren't really looking, they were looking at this. You know what else they were thinking about? They were thinking about UBVRI. And that, my wonderful students, I love, love, love. You know why? Because this student put together this diagram and this code and this sentence, and then, and got 4 points, and they put together this diagram. That was the cover, the second cover page. So they were thinking about they were thinking UBVRI. They were thinking colors, basically. They were thinking color indices. And basically, they were thinking, okay, Procyon A's peaking in B, Sun's peaking in V. Okay, that settles the matter. So that was lovely. And it shows me that student is thinking. They're putting together stuff. Right? And that's, I spent like a half an hour talking with a student yesterday in office hours about that. How do you study and what, how do you put together a good exam? And I said, to really crush an exam and to ace it, and I don't know if this student aced it, but to ace an exam, you got to be able to think. And when I say think, I mean you're either putting together two different things, like this spectrum and the UBVRI chart, or you're taking this spectrum and pulling it apart and making a decision, all right? Or you're doing a combination of both. Now here's another student's code, and I want you to look at this one. Here's their code, PRL. Almost everybody started with the letter P, Procyon. They were focusing on Procyon, which is good. That's the top curve in this spectra. PRLWY, DQL. Have your clickers ready because we're going to do a clicker question in just a second. Now, here's the straight decode with all the parentheses and stuff. A little bit shaky looking. But through my superior strategy and human intellect, I can clean it up. And here's it's still not, ultra graceful, but it's workable. Procyon A's filter band V wavelength is larger than the sun's filter band B wavelength. All right, now this one got a partial credit, 1. And in other words, it's not correct, but they were thinking filter bands B and V. And that's a normal thing to do when you're looking at these two stars. Now, if we had Alpha Centauri C, which is a little red star, you know, and looking at, so like looking at the sun and Alpha Centauri C, you might have been thinking, what's the R or what does the I band look like? All right. But for these two stars, it's natural. So they were thinking filter bands, good. But they didn't quite get it right because the filter band wavelength, I think they're talking about this peak wavelength, but they didn't, let me get my cursor over here. This peak wavelength, I think that's what they're thinking about, but they didn't use the word peak wavelength. They did something else. All right, filter band V wavelength. And same over here with sun's filter band B wavelength. So this was a little shaky, and this is an example of a student. I gave him partial credit because they're thinking filter bands, and that's good. And the previous question, the student executed or made a decision and wrote a sentence thinking in terms of filter bands, and they got full credit. So, so this one I gave a little bit of pointage to. All right, and you're going to be grading one here in just a few minutes using your clicker. So, be ready, Lexi. Be ready, everybody. Here we go. Now, here's another one. Question: why can you conclude logically that Procyon A has a higher surface temperature than our star, the sun? Now, here's another really long one. PJL, WY, VT, DJL. And here's the straight decode with all the parentheses and stuff. And here it is, tricked out a little bit better. Procyon A's peak wavelength is larger. Stop right there. Procyon A's peak wavelength isn't larger. It's a smaller wavelength. You look at that, it's 438 nanometers. Earth or sun's is the bigger one. So that one right there is wrong. And so that one got a 0. All right. So I want you to remember if on the final you have a sentence formation task about like this or like something else, I want you to think carefully and write your sentence. Take a minute to figure out a good sentence and try to write it as gracefully as you can, and then hit the symbols and then hit the send key. And be encouraged that you may not have the same sentence as somebody else, but you can still get full points. And you might get 1 point or 2 points or 3 points. I got several students in each of those partial credits. So now I want you guys to make a clicking decision, and you're going to make the call on the following code sentence. All right? And go ahead and start the question. Here's your... This is another one. It's a little shorter. PJWYD. Procyon A's peak is larger than the sun's. Here's the cleaned up version in yellow. Procyon A's peak is larger than the sun's. So how would you grade that? Go ahead and vote. Let's see the... no, it's short answer. So go ahead and do this. I want everybody to. That's why it's short answer. See this? Talk it over with your neighbor if you want, see if they disagree with your grade. You're the grader today. You're grading your classmate's exam. I don't know who this is, but somebody sent this in. 30 seconds.
There's a question.
Where? Oh, yeah. Hit the bring it up here. Come on around up here. Take a look at it. Was it working on the exam? Your batteries might be flaking out on you. Let's take a look here.
I got the message.
Yeah. Dude. All right, let's try this again. Good. Good. So what's the just type in a letter.
And then do the send.
And then hit send. Yeah, for this one, you guys, you have to hit the send key. So type in your, I'm sorry, I should have mentioned that. Type in your letter and hit the send key. Okay, so which letter do you vote for? Then you'll get it. Type in your letter, hit the send key, and then you'll get a check mark. All right? Okay? Yeah, good. You're welcome. Good. All right, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, show the students this one. Now, if you look at that, you'll see that we have a little bit of explaining to do. And look at that. Oh, you guys are mean. The biggest group, it's not a majority, but the biggest group gave the students 0. Gosh. All right, go back to regular display, please. You know what I gave that student? Ching! 4 points. So, now, just so you know, that particular question, I gave everybody correct on it. So, so if you voted for A, B, C, or D, and not E, you're still going to get correct on that one. Okay, it's kind of like a survey. But yeah, that's a 4-pointer there. And you know why is that? Everything on that spectrum of Procyon A is above the sun. All right? So that's an acceptable answer for that particular question. All right, let's hand back exam printouts now. And we'll do some more clicking, so don't put your clicker away. But what we're going to do is pause the podcast. And then we're going to get my cursor back over here. Okay, let's keep going. As always, just to remind you that the score on your exam printout is just part of your exam for grade. The clicking is up. The clicking points are up. I did that last night. I had a marathon grading session yesterday. Finally got it up before I left campus. So that plus what you have in front of you, other than, if you have a blank or a double, we're checking that right now. But those add up. Now, another thing I want to mention to you is now almost at 80-something% of you have got 3 exam scores on the books, all right? And I'll activate your Scantron score in web courses this afternoon about 3 o'clock or so. So you'll see, you have your printout, and you'll see it in web courses this afternoon. And most of you have got, a huge proportion of you have got 3 exams, and now we can think about the best 2 out of 3 maneuver. And I'll try to do that this weekend. And you may have noticed I've already put a row in your grades page for the best 2 out of 3. All right, and I'll do that for everybody. As soon as we get all these bloopers and stuff figured out, The people with messed up PIDs and whatnot. All right, so we'll try to do that as quickly as we can. And then we're clicking today. You know what I'll try to do today? I'll try to do a clicking roundup as of today, November 16th. And so you'll be able to get another estimate of your, how many out of 45 you've got. And then you'll have a fairly good idea. We've just got a few more classes now. We're going to be clicking. We're going to be clicking today, a few more clicking questions. And we're going to be clicking next Tuesday. So if you're planning to slide on out of town next week, we're going to be doing clicking and a regular lecture on Tuesday. All right, and then when we get back after Thanksgiving, a full week of lecture, and then finals week. So, you know what? I have talked to many of you over this semester, a little bit or a lot. Some of you in web courses, some of you in person. And I have to say it, and I say it every semester, and it's true every semester. I've had a lot of fun. I've enjoyed every minute with you guys. Well, almost every minute, except when the machine up here doesn't work. But yeah, I've really enjoyed it, and getting to know some of you that are interested in astronomy, and those of you that are just trying to, get a good grade and get this checked off on your requirements and stuff. I just want to say it's been fun, and thank you. It's my pleasure and my and if I have your vote in November. Anyway, that's good. All right, so let's keep going. I want to talk about the end state of stars that are, right now on the main sequence. The main sequence is most of the stars that we see in a galaxy or in a cluster. All right? But there's plenty that are off the main sequence, and how they exit the main sequence, it can be compared to, retiring. Retire and move to Florida. All right? Now, I want you to look at this diagram. This is figure 4 from chapter 22. So that clues you in that we're in chapter 22 and stuff. Chapter 22 concepts. This is on the right an image of a star cluster. It's kind of an open cluster. It's called M41. It looks like a fuzzy patch, a nebula on the sky, but it's actually a cluster. And it's interesting because this cluster, we can get the luminosity, the apparent magnitude, and the color for everything in this cluster. And because they're the same distance away, for the most part, a little bit of plus or minus, but just a small amount of plus or minus within the cluster, we can make an HR diagram for those. And that's what we've got on the left. All right, now this one we actually know what the luminosity is. All right, and so you can see that, let me get my cursor over here, there's some red giants over here to the right of the main sequence. But right about here, they start easing off the main sequence. The main sequence being the red line there. And that's the theoretical main sequence. All right, and then, so right about there, and then they rapidly, they're heading over there to red giant country. And a couple of these, like this one here is still kind of poking its way over. But they move pretty rapidly from over here, and then in a few thousand or a few million years, bam, they're over here in red giant territory. Now, we're going to be talking about that because the reason for this point, this is called the main sequence turnoff point. You know, where the stars, you plot them up, and this one's, it's not quite on the main sequence. The one furthest down off the main sequence, where it kind of makes a little corner, Michelle, you know, that's the main sequence turnoff point, and that's really important. That's what we're going to talk about. Now, here's a theoretical main sequence, and a few stars sprinkled in there. And we know that from numerical modeling, you know, doing all the physics and the nuclear reactions and stuff, we can figure out the lifetime of the high mass stars up here, 60 times the mass of the sun in the upper left, the hot blue stars. And then here's the sun down here, 1 solar mass. And then here are the really little ones, the red ones, lots of them, 0.1 solar mass. We can figure out theoretically how long they're going to keep fusing hydrogen. We know about how much mass they have. We know the strength of gravity. So we have a fairly good idea of the temperature in the core. And we know that, you know, for instance, the sun, we worked it out, you know, from its luminosity, how much mass does it convert into pure energy? And it's a fairly small fraction. And that's basically what this diagram tells you. So you can look at something on the main sequence and you can say, okay, upper left, up there in the blues, spectral class O, we're talking maybe 10 to the 7 years. That's 10 million years. And in the time scale of the universe, that, my friends, is a blink of an eye. Those things are like firecrackers compared to the age of the universe. You know, the universe is about 14 billion years old, we think. Okay? And this is actually one of the ways we gauge that, by knowing this stuff here. We know what's happening in our galaxy, and we can think about other galaxies and way back in time. And yeah, so these things are they're so big and they're so hot that they're going to nuke all their hydrogen in the core in about 10 million years. Now, for us down here, the sun, we estimate, okay, sun's doing good, not that fast. It's kind of a medium-sized star. And so theoretically, the estimates are about 10 billion years, 10 of the 10 years. And then these guys down here, 10 of the 11, oh my goodness. 10 of the 11, that's 100 billion years. So these things are still going to be around, cooking, nice and easy, till the cows come home. You know, well after the universe is aged and all the other things are off the main sequence. So the sun is going to be off the main sequence and it become a white dwarf, basically, well before these guys even think about it. So, all right, now, so up here, go ahead and make a note. 10 million years up here, about really fast evolution. And they got a lot of mass. They're going to be a big star, maybe a supergiant, big red supergiant. The sun, 10 billion years, and then these guys down here, about 100 billion years. All right, so this is kind of a theoretical HR, and it's tricked out with some colors and stuff like that. But the main thing here is that this theoretical HR diagram allows us to figure out the age of a cluster. If we can get a fairly good HR diagram for a cluster of stars, in other words, measure the color and measure the apparent magnitude, if they're close enough for that, then we can actually figure out the age by looking for that main sequence turnoff. So here's another example. This is a star cluster called M55. And that's named after all these M's. They're nebula and objects in the sky other than a star. They were cataloged several hundred years ago by a French guy named Messier, Messier. And so they're called Messier objects. He just made a list of the ones that he found. And this is the 55th one that he cataloged up. The Andromeda Galaxy is M31, 31st one he got. So he's got, different nebulas and clusters and stuff like that. Right now we can date this thing. It's a globular cluster. It's in our galactic halo. So it's not in the disk. It's orbiting the nucleus of the galaxy down there where SGR A star is, that big black hole. And it's way out there. It orbits as a big cluster, a big blob of stars. So this thing is enough mass to keep itself together as a cluster as it moves, kind of like the solar system. The solar system is moving through the galaxy. We're in the disk, but we're orbiting the galaxy, but we stay together as a solar system. The same thing here. This cluster, M55, and all the clusters that we see in the galactic halo, they're orbiting the nucleus of the galaxy, and they stay together as a blob or a cluster of stars. And this one we figure has got about 100,000 stars. So it's with good telescopes, we can get a color and an apparent magnitude. All right? And so we can estimate the age of this cluster by looking at its main sequence turnoff. What is missing? And here's another way to put it. And I like Roman numeral 4 here. What is missing from the main sequence? All right? If it's 10 million years old, then all the blue stuff at the upper left up here in the main sequence is going to be gone. All right? If it's 100 million years old, a few more stars down the main sequence. If it's 1,000 million years old, in other words, 1 billion years old, a few more stars, getting down towards the white stars in the main sequence. They're going to be missing. They're going to, be up there in the red giant or the supergiant branch somewhere. All right, so we're able to figure out an age by looking for the main sequence turning point, or by just kind of figuring out what's missing. All right. So here's the everything good? Yeah. All right. Any changes?
Yeah, do you want me to mark it?
What's that?
Do you want me to mark it?
Yeah, mark it on this stack over here. All right. Here's the HR diagram for M55. I don't know, maybe make a sketch of that. And you can see here's some, and this is slightly different. This is visual absolute magnitude. So this is the V filter over here, and down here is B minus V color index. So the red stars are still on the right, the blue stars are over on the left. And this is for the cluster M55. So right about here is the main sequence turnoff. So you have to ask yourself, okay, how old are these things? They're about to hit they're about to exit. They're about to retire and move to Florida. So here's Florida up here, okay? All right, and then where else do you retire? San Diego. You move to California. So here's San Diego, California. These guys are retired up there, and these guys. But there's a little bit of scatter in it. But so here's the main sequence turnoff. All right, so kind of make a sketch of that, or just make a note M55, and the main sequence turnoff is about 12.5 billion years. All right, and all the stuff down here is going to take more than 12.5 billion years. Let me ask you this. Is a G-type star like the Sun still on the main sequence in M55 or off? What would it have to be? Off or on? On or off? Think. Main sequence cutoff is 12.5 billion. So that's how old this cluster is. What's the estimated lifetime of the SUN? G2 star. Oh, you guys are slacking here. About 10 billion. All right, so the sun is already off, or stars like the sun. They're already out. They're already retired. And I'll tell you a little story about this. This and other globular clusters. We've known for a while that these globular clusters were about 12 upwards of 10 billion years old. And so it's a fairly reliable way to estimate the age of a cluster. A completely separate measurement is the age of the universe itself. That's based on the Big Bang Theory, and it's based on the what we call the microwave background radiation that we see everywhere in space. That's basically a photon gas that has cooled as the universe expanded, and by looking at the spectrum of that microwave radiation, we can estimate the age of the universe. Now, when I was in grad school in the late 90s, they were still making, a matter of fact, I was at a conference, a black holes conference, and Stephen Hawking was there and stuff. I never met him, but I mean, I could see him. Listen to a talk. And we were at this black holes conference, and up in Canada. And all the big shots were given papers and stuff, and I was I was a grad student, so I was, even my advisor wasn't a big enough big shot. But anyways, we were up there, and at that time, the Big Bang Theory, our measurements of the CMB, the cosmic microwave background that they discovered in the 60s, led to an age of the universe about 10 billion years. All right, now that's a problem, because these globular clusters were older than that. And so we had a problem. In the late 90s, we were looking at the Big Bang Theory, and we were looking at globular clusters, and we were thinking, how the heck can you have a globular cluster that's older than the universe itself? Something doesn't compute. Now, what didn't compute was the fact that our observation of that microwave radiation background was not very precise. So in the mid-90s, they launched this satellite, well, the early 90s, I guess, called COBE, C-O-B-E. And it was Cosmic Something Background Explorer. And it measured the background radiation, and from that we got an estimate of the universe, the age of the universe, and by God, it was older than the globular clusters. And I remember when it came out that very day, they released their results. We were at that conference with Stephen Hawking and all those guys, and oh my goodness, it caused I'd like to say it caused an uproar, but those guys, they're kind of nerdish, so they don't really get in an uproar about stuff. But it was like a beehive, everybody's talking, oh man, this is cool, and it just was really exciting. And so now we've reconciled. These things are old, and we now know that the universe is even older. Good. Because for a while there was something didn't make sense. So here's another way to look at this. In M55, this one here, the 10 million year old stars are gone. They're up somewhere in the upper right, or maybe in the blue group in San Diego. The 10 billion year old stars are gone because the cutoff for M55 is about 12.5 billion years. So All this stuff down here in the red, that stuff is still cooking because it's going to take 100 billion years or so for those things to jam off the main sequence. And then when they do, they're not going to be easy to observe at that. So now, here's the logic. I pulled a quote from chapter 22, section 3. And this one kind of tells you the logic of the main sequence turnoff. This means that no stars are left near the top of the main sequence, just like M55. Only the low mass stars near the bottom remain. M41, M55, all the clusters, we can usually see that. The older the cluster, the lower the point of the main sequence, and the lower the mass of the stars, where the stars begin to move toward the red giant region. In other words, the main sequence turnoff point. Right? The older it is, the lower down towards the M red stars that you're going to get. And M55 is a pretty good example of that. So go ahead and make a note of that. That's from chapter 2, section 3. And that basically gives you the logic of why we care about the main sequence turnoff. And remember those big HR diagrams that I showed you for Hipparcos and for the Gaia satellite? And we saw a big, mighty big turnoff to the red giants area for those. So that point, the main sequence turnoff, is pretty important in general. Now, they're moving off to retirement. You know what exactly happens? Well, for a low-mass star like the Sun, and get ready for a clicker question in just a minute, the stars are going to leave, if it's a smaller star, it's going to leave the main sequence. It's going to expand to giant star status of some kind, and that's because it's going to start fusing helium and other elements, like silicon and carbon and stuff like that. Now, when they do that, they expand, so they get bigger. The further away the surface of the star is from the core, the weaker the gravity. So the outer shell or the outer layers of the star can be unstable. They can be blown off, right? And we see this all the time. It's called a planetary nebula, and this is an example. Now, it's not planets. It looks like planets going around and around a circle. So that's how somebody in the 1800s decided to use that term. They're not really planets, but we call them planetary nebula. It's basically the outer layers of a giant star getting blown off, either violently or gradually. And actually, our star, the Sun, is blowing off very tenuous amounts of mass from its surface, and that's called the solar wind. All right. Now, a red giant star, when they change rapidly, they can, blow off big amounts, like a super duper solar wind event. Now, the leftovers is frequently a really hot core. So the star will, if it's a fairly small star, it'll blow off layers, form planetary nebulas like this, and then a white dwarf will remain. And the white dwarf, the core, is possibly about the size of the Sun, and you can see it in the center of this image. And it's going to be so hot that it'll be really bright in the ultraviolet. So the U filter will be getting most of the light from those white dwarfs. And on the I filter, you might get a little bit, but nothing great shakes. Here's a close-up. This is NGC 6369. Go ahead and make a note of that. You can look at it later. And just type in the word planetary nebula inside Google, and then click images, and you'll see buku images. There's the white dwarf at the center. And right here is an expanding layer, that we've studied fairly closely. And a lot of times you can see different layers. So different events, the core of the star gets unstable slightly, heats up a little bit too fast, blows a few outer layers. Then it stabilizes, and then something else, they start cooking silicon, and It gets unstable at the core slightly, and then the outer layers of the star get unstable. You blow a few more layers. Here's another one. This one's called the Bubbly Nebula. All right, and you can see the central object right here. Pretty bright. Here's one that you guys saw at the observatory, the Ring Nebula. Go ahead and make a note of that one. That's a famous one. And you can see it at the, and hey, you guys, after Thanksgiving, there's one more Nights Under the Stars extra credit opportunity. And hopefully you'll be able to see the Ring Nebula. And now you'll know what we're talking about. And I know a bunch of you have gotten to the observatory and you're wondering, hey, Dr. B, what are my points going to be going up in the grade book? And if you were in my office, as some of you were the past few days, you'll see a big stack of the observatory handouts that I still haven't put in the grade book, but I will. So, Ring Nebula. Here's the central object. You can usually see it. Here's something called the Helix Nebula. Kind of cool looking. Yeah, so these are planetary nebulas, and it's just a star blowing its layers. This one looks a little more catastrophic. It also looks like it has an axis kind of tilted at 45 degrees. That might be the spin axis of the star. I should look that up. Here's another one. And you can see the central object here. Now, clicker question. Ready? Multiple choice, please. What is the sun considered? Go ahead and vote. A, B, C, D, or E. And there's a picture of the SUN. And hopefully this will be actually, this is kind of interesting. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Oh my goodness. Go ahead and let's display this. Tricia, if you please. Yeah, the correct answer is A, low mass star. The other stars, what this means is it's never going to become a black hole or a supernova, as we'll talk about in a minute. Go ahead, move back to the regular display. And so there's your answer. Now, what we're going to do next time, I'll give you a reading assignment this weekend. Look for it tomorrow sometime. And I'll be giving you some reading about the element iron and supernova explosions. Okay, you're dismissed. Come on up if you want to get your printout.